All right, what's going on, everybody? In this video, I am going to give you an introductory topic and just talk about stress. And here, stress is by definition in lots of textbooks, is the intensity of force per unit area. And, units of stress are things like PSI, pounds per square inch, pascals, which is a Pascal, which is equal to 1 Newton per 1 Pascal is 1 Newton per meter squared. Anyways, it's essentially the units of stress are force divided by area here. Okay, but really, stress is I look at it like a way to normalize force. Okay, so how can we compare apples to apples? Because sometimes we'll ask, how much weight can I carry versus how much weight can you carry? And really that what matters there is, it's not exactly about weight, but it's more like, what am I made of? What are my bones made of? Do I work out? Do I have more area than you or more mass so that I can maybe possibly carry more? Or probably you have more mass than I do that you could carry more. Who knows, right? So it's more like, um, the question would be like, how much stress can he handle? And so maybe you can give him more work, right? Or more weight. Anyway, I look at it as a normalizing thing as opposed to it's just a way to normalize force so that you can compare apples to apples between materials, between structures, whatever it is. So the concept is kind of it's cool. You got a body here, so this is a body here, and let's make it a human body. That way you can relate this to something more tangible, if you will. So here I've added legs and arms to my potato here, so it's an awkward potato, but nonetheless, and there's a lot of external forces going on this person. External forces pulling on someone, extending someone, whatever, right? You know, um, and if I look, these are all my external forces. And if I make a cut and I want to look on the inside and see what's going on, what's going on, what's holding this body together? I've got muscles, I've got bones that have forces going on, acting in all kinds of directions. And each of these little internal forces represents, um, something inside my body that is carrying a load. All right, so if I look at this little increment of area right here, if I zoom in on this little increment dA right here, this is dA, I've got this force here, this incremental force acting on this area, dF. I'll just call that dF right here. And if I assign a coordinate system to this element right here, I say, shoot, here's Z, here is, let's see here, let's call this X over here, Y, Z right here. And I can break up this force vector into components right here. Okay, I can break it up into components. Here, this would be dFx. There'd be a vertical or a z component dfz, this vector here, and then dfy right here. And and each of these forces acts on this, each of these increments of forces acts on this area, and it induces a stress, this intensity of force per unit area. And really, there's only two types of stress, two types, okay? Every force results in either one of these two types of stress, all right? And the first type is a normal stress, not because it's normal, because it's normal. Because it's perpendicular, right? Not normal as in like psychologically normal, but like normal as in it's perpendicular to this area dA. It's normal to the surface. So here, this sigma, we use the symbol sigma for normal stress, any normal stress here. And that would be, in this case, if you use like calculus convention, as dA goes to 0 and all this stuff, the limit right here, it's this dFz divided by dA, okay? This normal force over the area right here. And then the shear stress, there's going to be two shear stress here, shear, and just like scissors, it's just shearing the surface, okay? So it's running parallel, it's like rubbing against dA, shear scissors, shear stress right here. And this tau, there's actually two shear stresses on this right here. We have a shear stress that's on the, if you will, the Z face acting in the X direction. Okay, so we're on, that's later on. But here, this shear stress on the Z face acting in the X direction, that would be limit again as dA goes to 0. of dFx over dA right here, okay? So that would be the shear stress, and then another shear stress would be in the on the z face in the y direction, and that limit would be dA goes to 0 dFy over dA. Okay. Now, this is, this you're going to come back to this later on as you get more and more into mechanics of materials. But this is just to give you a sense of I have all these forces here. I got these internal forces going on. I have if I zoom in on a single area, I apply, I look at this little incremental force, the internal force, the guts, if you will, my cartilage that's holding my body together, or my muscles together, my muscles that hold my body together, something, right? But it has some force here, something there that has internal force, and I can break it up into components, and it's inducing a normal stress or a shear stress. Okay, that's what you have to know. We have two types of stresses, shear and normal stresses, but the key here, especially in the early going of mechanics to materials, is to be able to take what you know as internal loading, okay, internal loading, and calculate the stress associated with each internal load. And so internal loading was, you might have seen in statics or something, uh, you had like maybe a cantilever beam here, cantilever structure. It doesn't have, beam doesn't, I don't know, with cross section could be circular, rectangular, who knows, whatever, I-beam, whatever, right? And maybe you have all kinds of loading going on. You have like a distributed load, W, you have an axial force, we'll call that P, uh, maybe even some sort of twisting action going on. Call that blue right here. So we'll call this like a moment about X, okay, some sort of twisting action, all kinds of things going on. And one basic problem was to calculate here, maybe the internal load at A. Okay, so call that point A. And one question is, what's the state of internal loading at A? And what you had to do, or what you want to do, is make a cut. We want to make a cut right here. We make a cut, and we have this, we draw the free body diagram of that cut right here, and we have internal loading that which when we draw in its positive sense, we have a shear, bam, and maybe an internal axial force, maybe even a moment right here, and then maybe an internal torque, call that T right here. And in mechanics, each of these, V, M, N, and T right here, the torque, the axial force, the moment, and the shear, induce either a normal stress or a shear stress. So here, and just to put it into a nutshell, some equations that you're going to get to later, this moment right here, so this normal force, as you can imagine, induces a normal stress. So here, if this cross section right here has some area A right here, and a moment of inertia, we'll need that later, I right here, okay? The normal force right here induces a normal stress. Sigma is equal to N divided by A. Okay, and then here, this moment, which is a bending, it causes, if you remember, a couple, it causes compression on one side, tension on the other. It also induces a normal stress, which we use this formula called the bending formula minus my over I. And this is, again, for later, okay? So this is kind of mechanics in a nutshell, at least some of the core equations right here. And these are my normal stresses. So here, as far as we're concerned, for most of an introductory course in mechanics of materials, the only things that induce normal stresses are the normal force and a moment, okay? The shear force, as you could imagine, induces a shear stress, okay? Shear stress here, and in a bending or beam bending situation, we'll talk more about this later, is VQ over IT. We'll talk about what that equation means later, okay? But this is a shear stress formula for transverse shear, okay? And then here, the twisting action here, twisting just like when you're twisting chalk, right? And you'll say something like, it's sheared off, man, right? Well, here, this tau is equal to T rho over J. J being what's called this polar moment of inertia. T is the internal torque. And here, this torque and this shear force, this internal shear force, induces shear stresses on this at point A, okay? And this moment and axial force, N, induces normal stresses at this cut at A, if you will, all right? And that's really essentially mechanics of materials, and these are really the most crucial, these are the four crucial stress equations that you're going to be able to need to use, and that associate this internal loading to the appropriate stress. All right, so hopefully that gave you a little bit of mechanics of materials in a nutshell, and you enjoyed it. Let me know if you have any questions. I'll do an example on on finding internal load next. All right, take it easy. Bye.